Okay, let's close out this book with this last podcast. I will, as I said, I'll add probably some podcasts from David Nealon's book on modeling climate change just to see what additional points we can make. So are there multiple equilibria in coupled climate models? It turns out that there have been solutions in the current climate found by Suki Manabe and Ron Stufer of GFDL, for example, where they produced the observed circulation that exists with the Atlantic meridional overturning circulation, global conveyor belt, so deep water formation in the North Atlantic. But under the present climate itself, under certain conditions, they found that the North Atlantic had a Pacific-like circulation, and the explanation or the hypothesis is that under certain circumstances you can have a lot of freshwater flux in the North Atlantic, which makes it much more difficult for the deep water to form, and such a thing seems to have happened. The 8.2 year event that we mentioned before is something like that. So this is what we looked at before. In this chapter we are looking at paleo data for a short period going from 10,000 years ago to about 90,000 years ago, and we looked at the fact that the North Atlantic, Greenland, has these millennial timescale oscillations where there are abrupt changes. Warming happens in a timescale of a decade, and the cooling periods happen over multiple centuries and couple of thousand years. So on millennial timescales there are associated methane signals and CO2 signals and so on that we already discussed. So what about the current climate and the coupled climate models? First of all, coupled climate models have many more feedbacks, and it's not so easy to trigger multiple equilibria in full models as it is in the simpler models that we looked at. Plus, when you have global warming with the increased anthropogenic CO2 forcing, multiple things happen. One, of course, is that we are melting glaciers, especially over Greenland, which can potentially put lots of fresh water on the Gin seas, Greenland, Iceland, Norwegian seas, where deep water forms, and the warmer atmosphere also can put more rainfall, but it can also hold more moisture, so there are multiple feedbacks. In addition, if you look at the distribution of salinity, North Atlantic is very salty, especially if you compare the Gin Sea region and similar latitudes in the Pacific. Even though sea surface temperatures are much colder, this is the salinity map here, the fact that the North Atlantic is much more saline makes it easier for it to evaporate and then add some more salinity and create deep waters, which is what happens. So the mean conditions in the present climate are such that it's easier to form North Atlantic deep water, but similar deep waters cannot be formed in the North Pacific because it's just too fresh, even though it's much colder. So that's something that has to be kept in mind. Plus, there is also an exchange of water vapor from here into the North Pacific across the Asian landmass. And if you look at the surface temperatures, air temperatures, sea surface temperatures and air temperatures, you can see that it's much colder on here than here. So the temperature difference is not as dramatic from the North Pacific to the North Atlantic, but the contrast over the land over North America and similar latitudes in Europe is quite dramatic. So the air here is able to hold much more I think this is sea surface temperature and then air temperatures on land temperatures over the continents, because you can see the upwelling here, the Gulf of Mexico, Gulf Stream and so on. It just says annual mean temperatures Obviously it's mixing sea surface temperatures and surface air temperatures, but nonetheless those kind of things matter, especially when you look at simulations for the 20th century going into the future. So these are changes in the Atlantic meridional overturning circulations in 19 coupled climate models for the warming scenario A1B. So the older IPCC scenarios from CMIP 3 until year 2100, holding greenhouse gas concentrations constant thereafter. Mean models show a weakening, but the uncertainties remain relatively high. Some models do not agree with the observational based estimates, which are in the black vertical bars here. So many models seem to show a significant weakening of the meridional overturning circulation, but if you were to use observational estimates for the time period over which we have data, the models which are starting off very low or very high have to be dealt with some caution. The simpler models also indicate that slowing down of the thermohaline circulation or meridional overturning can collapse when it hits a threshold. So it's unclear whether, for example, this model, these are the various models, is collapsing rather quickly and then staying almost at zero, whereas there are others which are much more in the observed range and don't show a collapse even out to 2200. Some of them start in the observed range but show a more drastic reduction, and so on and so forth. Be as that may, there are simple models. So this is the Byrne 2.5 model, again for the evolution of the meridional overturning circulation in the Atlantic considering a warming scenario. So these are the PCO2 levels prescribed with 560 ppm held constant after some integration of close to 70-80 years, whereas others are increasing CO2 at 1% per year out to 560. Here it's increasing at 2% per year. The experimental numbers are noted here: 650F, 1% per year, 650 here, 750, 750S, and so on. And if you look at the maximum overturning in Sverdrups in these simulations, the different simplified CO2 scenarios consist of an exponential increase at different rates, leveling off at a given maximum value. The MOC reveals a bifurcation in its behavior, as you can see here, for small maximum values or slow rates of CO2 increase. The threshold for a complete shutdown may be avoided. Okay, so you can see that some of them collapse at high increases in CO2, but it can be avoided by making smaller perturbations of 0.5% per year. So you reach 750 but after a much longer integration, and this one seems to head down but then recovers. Similarly here, but this one collapses and doesn't come back, this one collapses and doesn't come back. So simpler models provide such collapse scenarios, but it's unclear right now whether the current climate with the global warming trends and the emission trends have any such solutions possible in the next couple of centuries. IPCC in 2007 stated, based on current model simulations, it's very unlikely that the meridional overturning circulation of the Atlantic Ocean will slow down during the 21st century. But this has already changed because many papers have been published that we are right now at the slowest meridional overturning circulation in more than 2,000 years or longer. The multi-model average reduction by 2100 is 25%, ranging from 0 to about 50%, so that's a large range. For special report on emission scenarios A1B, temperatures in the Atlantic region are projected to increase despite such changes due to the much larger warming associated with the projected projected increases of greenhouse gases, it is very unlikely that MOC will undergo a large abrupt transition during the 21st century. Longer-term changes in the MOC cannot be assessed with confidence. This basic assertion has not changed much in the latest scenarios or assessment reports, so we are still not sure that with the emissions and warming rates there is an imminent collapse of the meridional overturning or complete disappearance of the Greenland and substantial sea level rises beyond few meters, for example, and even there are large uncertainties. Nonetheless, one must keep in mind that the Greenland melt extent and melt rates are accelerating. So this is the melt extent in percent average of 1981 to 2010, median, and interdecile range and interquartile ranges are shown here in terms of estimates, and the 2021 melt percentage is substantially out of the window of this range we have for the last 3 or 4 decades. So one has to be careful to see whether we are kicking now the giant, the climate giant, fairly seriously. When we look at the temperature trends, there is the strong polar amplification in the polar Arctic circle. Southern Ocean doesn't show such a strong polar amplification. Land warming is larger in most places than the ocean, but most importantly, there is a warming hole or even a cooling happening in the North Atlantic region where the North Atlantic Deepwater Formation happens, and there is still a debate about whether that contribution is coming from the meridional overturning circulation and the cross-equatorial transport changes, or it has something to do with the transport changes happening to the north of the Jim Seas, Greenland, Iceland, Norwegian seas. Nonetheless, this is obviously an indication that there are probably changes in the Atlantic meridional overturning circulation that are contributing to the local trend here, which would be consistent with the kind of changes we expect with warming, increased freshwater flux, and so on and so forth. Okay. There are also putative tipping points in the system that are argued by some groups. So they include things like irreversible changes, tipping points, thresholds, switches, and so on in few phenomenon like the El Nino Southern Oscillation, methane clat rates getting perturbed and releasing large amounts in a short time, Southwest North America going into a permanent drought-like situation, Amazon rainforest collapsing, West Antarctic ice sheet collapsing. This is now being argued more and more based on data that this is much closer to collapse than we expected. East Antarctic basins, marine biological carbon pump, whether it can collapse and the ocean becomes a net source rather than taking up carbon dioxide. It takes up about 25% of the anthropogenic emissions right now. So will that collapse? Will tropical coral reefs collapse? Will Indian summer monsoon collapse to make India a desert? West African monsoon changes, dust sources, Sahara greening, Sahara drying. These things have happened in the Holocene. Around 6,000 to 9,000 years ago, Sahara was green. Atlantic thermohaline circulation we talked about. What the jet stream will do, the debate continues about whether Arctic sea ice loss and Arctic warming is making the jet stream more wobbly and bringing more extreme events all the way down into the tropics, for example. Whether Greenland ice sheet is has a pathway in which it may completely collapse or substantial part of it may collapse. Arctic sea ice disappearance seems much more likely, just the way it is going and the way warming polar amplification is happening. There are ideas about boreal forests being near tipping points. Yadoma permafrost. Permafrost is discussed a lot, but there are also complications there. permafrost hold, a lot of methane, and rapid release of that can have a significant positive feedback, and there are methane clathrates here as well. So these are kind of potential tipping points in the system. It's not at all easy to say how close we are to them or whether they will happen in the 21st century at all, but nonetheless one has to keep them in mind. The colors here are in the Köppen climate classification, which uses temperature, rainfall, and so on to create classifications like this: dry winter, dry summer, wet winter, wet summer, and so on, and various vegetation types. I won't go into the details, but potential shifts in the ecosystems can also have collapses or tipping points in them that are not very easy to predict at this point. So the main point one would leave with is that the current climate has multiple equilibria anyways related to maybe freshwater fluxes to the North Atlantic, but with the increasing anthropogenic emissions we are potentially pushing some of the systems towards their tipping points, like the Arctic sea ice, Greenland glacier, and so on. So this is a hot field of research, and newer and newer results keep coming out. So I will add a section called New Findings, where I'll keep adding any new results that are worth reporting under this course with climate science and climate modeling, okay, including modern climate change. So let me leave this here with Tom Stoker's book and then come back to David Neelan's book with some additional points that I think are worth making. Okay,